Welcome to The Explainer. Today, we're not just scratching the surface. We're going on a deep, deep journey into the very architecture of our connected world. We're going to explore what is, without a doubt, the most important transformation happening in telecommunications right now, the rise of O-RAN. And more specifically, why the year 2025 is shaping up to be this incredible, decisive turning point. We're going to push way past the buzzwords you might have heard. Instead, we'll trace the real, practical journey a piece of network technology has to take. We'll start in the controlled, almost sterile environment of a test lab, and we'll follow it all the way until it becomes a living, breathing part of a global network, a network that's increasingly being guided and optimized by artificial intelligence. You know, this is the moment where all the theory, all the years of hard work and standardization committees and late nights on open source projects finally comes together into something tangible, something real, something that will be rolled out on a massive commercial scale. So whether you're an engineer deep in the telecom trenches, a software developer building the next generation of cloud-native apps, or maybe you're just fascinated by the invisible infrastructure that powers everything we do, you are in exactly the right place. We are going to unpack, piece by piece, exactly how this incredibly complex, multi-vendor ecosystem is rigorously tested, how it's fundamentally secured, and how it is ultimately automated at a scale that, honestly, was thought impossible just a few years ago.
Okay, so to really do this topic justice, we've laid out a clear roadmap for our deep dive today. It's a logical progression designed to build our understanding from the ground up, one layer at a time. First, we'll start with the big picture, the why now. We'll dig into the O-RAN 2025 tipping point, looking at this unique confluence of events that makes this moment so critical. Then, we're going to roll up our sleeves, conceptually speaking, and build a virtual testbed, piece by piece, so you can see all the essential tools of the trade. Once we have our lab environment set up, we'll zoom in on something absolutely critical, security. Specifically, how we protect the airwaves themselves by verifying RRC integrity. From there, we'll pull the lens back a bit to look at performance under pressure, talking about stress tests, security scans, and software vulnerabilities. All of this leads up to the main event, connecting all that rigorous testing to the ultimate goal, which is a fully automated, AI-driven network. And to wrap it all up, we'll take a really pragmatic, honest look at the challenges that are still out there, and of course, the immense new opportunities that this new architecture is creating. This is our journey for today, so let's get started.
All right, let's really set the stage. Why this intense focus on the year 2025? What makes it so special? Well, it's because the story of O-RAN isn't about one single invention or some solitary eureka moment. No, 2025 represents this incredibly powerful tipping point. It's a moment where multiple different streams of development, things that were happening in parallel in global standards bodies, inside open source software communities, and in the boardrooms of the world's biggest carriers, are all flowing together to create this tidal wave of change. What we're witnessing right now is that critical transition of O-RAN from just a promising idea talked about at conferences into a large-scale, verifiable commercial reality. And on the next slide, we're going to break down exactly what those converging streams are.
This timeline really illustrates the perfect storm that's fueling all of this momentum for O-RAN. Let's really unpack each one of these points, because every single bullet represents a monumental effort. First, you've got the 3GPP. Now, for anyone who's not deep in the weeds of telecom, the 3GPP is the global standards body that defines the very DNA of mobile technology. We're talking about the fundamental rules for how your phone talks to the network. And in 2024, they're finalizing Release 18, which is better known as 5G Advanced. This is foundational. This isn't just a minor update. Release 18 is specifically designed to introduce and enhance features for RAN intelligence, for automation, for energy savings. These are the very things at the core of the O-RAN philosophy. A great way to think about it is that the underlying operating system of the entire mobile world is getting a massive update, an update that enables a whole new class of applications to run, and O-RAN is designed to deliver exactly those applications. At the exact same time, the O-RAN Alliance itself is hitting a new level of maturity. They're shipping new open-source software, the J&K releases, which are bringing more stability and a richer set of features. But even more importantly, they're hosting these global plugfests. A plugfest is exactly what it sounds like, a huge, collaborative, real-world testing event. You have dozens of vendors, companies that are normally fierce competitors, all bringing their shining new O-RAN gear to one location. And they physically plug it all together. They test to see if vendor A's radio can talk to vendor B's software, running on vendor C's cloud server, all following the O-RAN specifications. This is where the promise of a multi-vendor network stops being a marketing slide and becomes a real working system. It's how you build crucial confidence in the market. Then you see this huge step in what you might call institutional legitimacy. ETSI, the European Telecommunications Standards Institute, a hugely influential and formal standards body, is taking O-RAN's key documents and officially adopting them as publicly available specifications, or PAS. This move is a total game changer. It elevates O-RAN from being specifications created by an industry alliance, you might think of it as a club, to being a formally recognized global standard. Why does that matter so much? Well, for things like government contracts or large enterprise deployments, adherence to formal standards from bodies like ETSI is often a legal or procurement requirement. So this is a massive, powerful stamp of approval. And finally, you have the ultimate validation, huge investments from major network operators. When a titan like AT&T announces it's accelerating its large-scale commercial Open RAN deployments, that sends a profound signal to the entire market. This means real customer traffic. Your phone calls, your video streams, your data is going to be running over this new architecture. It's not a lab experiment anymore. It's not a small-scale trial. It's becoming a core part of a nationwide network. Honestly, any one of these 4 events happening on its own would be significant. But for them all to be happening together in this 2024-2025 window, well, that creates an unstoppable, self-reinforcing momentum.
Okay, before we dive any deeper into the tech, it is absolutely essential that we get our vocabulary straight. You're going to hear a few different terms used in this space, and the differences between them are really important. So let's start with the broadest concept, Open RAN. The best way to think about Open RAN is as the guiding philosophy, the big idea. For decades, the radio access network, or the RAN, that's the part of the network with the cell towers and base station gear that your phone talks to, was a proprietary closed black box. An operator had to buy the entire stack of hardware and software from a single vendor. The philosophy of Open RAN is all about breaking open that black box. It's about creating a disaggregated architecture where the different pieces of hardware and software are separated and defined by open, standardized interfaces. The ultimate goal here is to create a vibrant multi-vendor ecosystem, kind of like the PC industry, where you can buy a motherboard from one company, a graphics card from another, and an operating system from a third, and you're confident they'll all work together. It's a whole movement driven by the desire for more choice, faster innovation, and frankly, healthier competition.
So if Open RAN is the philosophy, you should think of O-RAN as the detailed engineering blueprint that makes that philosophy real. The O-RAN Alliance is the specific, global, industry-wide organization that's doing all the hard, detailed engineering work. It's the alliance that defines the concrete standards, the specific interfaces, and the reference software you need to bring that multi-vendor vision to life. So when you hear engineers talking about specific interfaces, like the O1 for management and operations, or the O2 for the cloud platform, or the absolutely critical E2 interface for near real-time intelligent control, they are talking about specifications defined by the O-RAN Alliance. It's this alliance that develops the open-source reference software we mentioned earlier and hosts those crucial plugfests. So in short, while Open RAN is the general dream of an open competitive market, O-RAN is the specific, technical body of work that provides the schematics and instructions for actually building it.
And that brings us to our third essential term, Cloud RAN. Sometimes you'll hear it called C-RAN. Now, this isn't about the philosophy or the blueprint. This is all about the deployment model. It answers the question of how and where the network's functions actually run. In the old way of doing things, all the complex digital work of the baseband processing happened in a specialized proprietary hardware box right at the base of the cell tower. Cloud RAN is this revolutionary approach of taking those really complex baseband functions, turning them into software, virtualizing them, and then running them on common off-the-shelf servers. And these servers can be located anywhere. They could be in a small data center at the edge of the network or even in a massive public cloud data center. This approach, which leans heavily on modern IT tech like software containers and orchestration platforms like Kubernetes, brings all the agility, the scalability, and the cost efficiency of the cloud computing world right into the heart of the telecom network. It's really important to get this. O-RAN and Cloud RAN are not the same thing, but they are incredibly synergistic. They work together beautifully. O-RAN gives you the open multi-vendor interfaces, and Cloud RAN gives you the flexible, scalable, software-defined platform to run those open components on.
Okay, so we've established this new world, a world of disaggregated components from all these different vendors, all designed to run as virtualized software on cloud infrastructure. This raises a monumental question. How on earth do you make sure that all of it works together reliably, that it performs under pressure, that it's secure from attacks? You definitely can't just plug it all into a live network and cross your fingers. No way. The answer always starts in the lab. It starts with the meticulous construction of a sophisticated, comprehensive, and repeatable testing environment, a virtual test bed. So let's do that right now. We're going to conceptually build one, piece by piece, so we can truly appreciate what it takes to properly validate O-RAN technology.
A truly robust and effective ORAN testbed is really built on 4 essential pillars. A good way to think about it is you're creating a miniature, self-contained universe that perfectly mimics all the key parts of a real mobile network. So, the first pillar gives you your population, the users, which are simulated by something called a UE emulator. The second pillar is the network brain, the command and control center, and that's provided by a 5G core simulator. The third pillar is, of course, the whole reason we're here, the device under test, or DUT, which in our ORAN world could be any combination of different components. And finally, the fourth pillar gives us observability, the eyes and ears, which are all the monitoring and sniffer tools that let you see exactly what's happening on the wire and in the air. Now, these 4 pillars aren't independent. They have to work in perfect concert to create a complete closed-loop system for doing really rigorous and repeatable testing. So let's look at each one of them a little closer.
Let's start with the first and most fundamental piece of our testbed, the UE emulator. In telecom speak, UE stands for user equipment. That's just the official term for your smartphone, your tablet, your connected car, pretty much any device that connects to the cellular network. Now, a really common question is, hey, why not just use a big stack of real phones for testing? And the answer comes down to 2 absolutely critical factors: scale and control. A UE emulator is a highly sophisticated piece of hardware and software that can realistically pretend to be not just one phone, but hundreds or even thousands of UEs, all doing very specific pre-programmed things. You just cannot achieve that kind of scale with physical phones. But even more importantly, an emulator gives you perfect deterministic control and repeatability. You can script these incredibly precise scenarios, like having hundreds of devices all try to connect to the network at the exact same millisecond. That's something that's physically impossible to coordinate with real devices, but it's absolutely essential for doing proper stress testing and finding out where the system's limits really are.
And when we talk about scale, we're not talking about just a few devices. This number here, 256, it represents a key benchmark in the industry for serious high-stress validation. An advanced testbed, the kind being used by the big labs and vendors, is capable of simulating 256 UEs, all trying to register with the network at the exact same moment. This specific and very punishing test is known as an attached storm. It's designed to create an absolute worst-case scenario. It puts the maximum possible stress on the control plane of the base station. That's the part of the system responsible for managing all the new connections. It's a brutal test for sure, but it's a necessary one, because its whole purpose is to find the breaking point of the system before it gets deployed into the wild. In fact, the software licenses for these powerful emulator tools are often sold based on how many UEs they can simulate. You'll see tiers for 8, 16, 32, and so on, all the way up to this 256 UE level for what's considered carrier-grade testing.
This quote just perfectly captures why a number like 256 UEs is so important. This isn't just some random number pulled out of a technical spec sheet. It is a direct simulation of a very real, very challenging scenario that network operators face all the time. Just picture it. The clock strikes midnight on New Year's Eve in a crowded city square. In a single instant, thousands of people pull out their phones to send that Happy New Year text or start a video call. Or think about the end of a sold-out concert. You've got 50,000 people streaming out of the stadium, and all of their phones, which might have been idle or on Wi-Fi, are now trying to reconnect to the cellular network at the same time. The local cell towers are instantly flooded with this overwhelming wave of registration requests. So what happens? Does the network handle it gracefully, maybe slowing down a bit but serving everyone? Or does it buckle? Does it crash and leave everybody with no service? The attached storm test, with our 256 simulated users, is exactly how engineers replicate that precise moment of peak chaos in a controlled, measurable, and repeatable lab environment. It lets them see exactly how their equipment performs under the most extreme pressure it's ever likely to face in the real world.
Okay, so we've got our army of simulated users ready to go. But in a network, they need someone to talk to. And this brings us to the second pillar of our testbed, the 5G core, or 5GC simulator. In a real 5G network, the core is the centralized brain. It handles all the high-level logic, everything from authenticating your device and checking your subscription to managing your data session and connecting you to the internet. For our testbed to work as a closed-loop system, we need to convincingly simulate this brain, and a 5GC simulator does exactly that. It provides all the essential network interfaces that the RAN expects to see, most critically, the N2 interface. The N2 is the control connection between the RAN, our device under test, and the core. By providing a fully compliant N2 interface, the simulator basically fools the DUT into thinking it's connected to a real, live network core. And this completes the communication loop. It allows our simulated UEs to go through the full registration sequence, set up a data session, and pass traffic, just like they would on a commercial network. Without it, the test would be fundamentally broken. It'd be like testing a phone that can't actually make a call. So now we get to our third pillar, which is really the star of the show, the device under test, or the DUT. In this new world of ORAN, the DUT isn't a single monolithic box anymore.
Because of that principle of disaggregation, it can be any number of individual components or combinations of them. Let's do a quick recap of what those are. The ORU is the radio unit. That's the part with the antennas that actually sends and receives radio waves. The ODU is the distributed unit, which usually sits nearby and handles the intense real-time baseband processing. And the OCU is the centralized unit, which can be located further away and handles the less time-sensitive, higher-level protocol stuff. A key strength of a well-designed testbed is its incredible flexibility. An engineer can choose to test just the ORU from a new vendor, or they might test an integrated ODU and OCU software package from another vendor. The testbed can adapt to validate whatever specific piece of this complex ORAN puzzle is under the microscope.
This insight here gets right to the very heart of why that flexibility is so absolutely critical in a multi-vendor world. Let's break this down with a really common, practical example. Imagine you're an operator, and you're trying to integrate an ORU from vendor A with an ODU from vendor B, and it's just not working. So who's to blame? Vendor A is going to blame vendor B's software, and vendor B is going to blame vendor A's hardware. You get stuck in this endless finger-pointing loop. To break that deadlock, you need what the source here so smartly calls single-point consistency testing. So first, you would test vendor A's ORU, making it the device under test, but you test it against a golden ODU simulator. That's a test tool that is known to be perfectly compliant with the ORAN standard. This completely isolates the ORU and lets you validate its performance and compliance all on its own. Then you flip the script. You test vendor B's ODU-CU combination, making it the DUT, but you test it against a golden ORU simulator. This methodical ability to mix and match real hardware with these ideal simulated counterparts is absolutely essential for pinpointing the precise source of interoperability problems. It's how you avoid that unproductive cycle of blame that can otherwise plague these complex, multi-vendor projects.
So, now that we've conceptually built our powerful and flexible testbed, we can actually start putting it to work. We can simulate hundreds of users, we can create a full end-to-end network connection, all inside a controlled environment. So, what's one of the very first and most fundamental things we should be testing for? Well, in any communication network, the answer has to be security. So we're now going to use this setup to do a deep dive into how an engineer verifies that the communication happening over the air, that's what's technically called the UU interface between your phone and the network space station, is properly secured. We have to be absolutely certain that the critical control messages that manage the connection are protected from being listened to or, even worse, maliciously changed. To be really precise here, our goal is to prove, with cryptographic certainty, that the network is correctly applying security measures according to the very strict rules laid out in the 3GPP standards. The messages we're most concerned with here are the Radio Resource Control, or RRC messages. It's important to understand, these aren't your voice data or your video stream. These are the underlying command and control signals that set up and manage your connection. RRC messages are what set up your call in the first place, they're what tell your phone when to switch to a new cell tower as you're driving down the highway, and they configure all the intricate parameters of your radio connection. If an attacker could intercept and alter these messages, they could cause huge disruption, from dropping your calls to maybe even redirecting your device to a malicious network. So to prevent this, we need to verify two distinct security services. First is integrity, which guarantees that a message has not been modified in transit, and second is ciphering, which means the message has been encrypted so that no one can read its contents.
To provide this protection, the 3GPP standards define a specific set of tools, the Network Integrity Algorithms, or NIAs. This table breaks them down for us. You've got NIA1, NIA2, and NIA3. These are all strong, well-vetted, standardized cryptographic algorithms, each designed to provide that crucial integrity protection. NIA1 is based on an algorithm called SNO3G, NIA2 uses the widely respected AES-CMAC, and NIA3 uses an algorithm called Zook. You can think of these as different models of high-security locks. The network and the phone negotiate which one they're both going to use for a particular session. But then, you see that first one on the list, NIA0, the null algorithm? And from a security point of view, this is the one that really demands our full attention because its name tells you exactly what it does.
The null algorithm literally means do nothing. It provides zero integrity protection. When NIA0 is active, those critical RRC control messages are sent in plain text, completely vulnerable, completely unprotected. Now, you might be wondering, why would such a dangerous option even exist? Well, it does have a very narrow, very specific, legitimate purpose for engineers during low-level development in a totally isolated lab. Sometimes, to debug a really complex protocol problem, you need to be able to see the raw, unprotected messages. But, and this is a huge but, If a device in a real-world network ever uses or is tricked into falling back to NIA 0, whether that's because of a software bug, a misconfiguration, or as the result of a malicious attack, it represents a catastrophic security failure. This is the digital equivalent of writing your bank password on a postcard and dropping it in the mail. So a primary, non-negotiable goal of network security testing is to rigorously prove that the system never uses the null algorithm in any normal operational scenario.
This slide clearly lays out the methodical, step-by-step process that engineers use to validate this critical security feature. This isn't guesswork at all. It's a repeatable, scientific experiment. Let's walk through it. In step 1, you prepare the test by configuring your simulators. You tell both the UE emulator and the 5G core simulator which security algorithms they should support and in what order they prefer them. For example, you might say, I want you to prefer NIA 1, but also be able to use NIA 2. This sets up the rules for the security negotiation. In step 2, you execute the test. You trigger the action by telling the simulated UE to connect to the network. And as that's happening, you use a network sniffer tool like the famous open-source program Wireshark to capture every single digital packet that's flying back and forth. In step 3, you stop the capture and you begin the analysis. At this point, you're basically a digital detective. You're sifting through that packet capture file, which is all the evidence you've collected. And finally, in step 4, you look for the definitive proof. You find specific messages in that capture and you look at their fields to confirm that the flags for integrity and ciphering were turned on. And most importantly, you check for the presence of a field called the MAC-I. The MAC-I, or Message Authentication Code for Integrity, is the cryptographic signature that proves the message is authentic and hasn't been altered. If that MAC-I field is there and it's valid, integrity protection is working. If it's missing, you've just found a serious security vulnerability.
During that analysis phase, testers aren't just looking at random data. They are hunting for a very specific conversation, a kind of digital handshake that negotiates and activates security between the network and the device. This slide lists the key messages that make up this critical exchange. First, the network sends a security mode command message. This is the network officially saying, okay, it's time to turn on security. Let's use integrity algorithm NIA2 and ciphering algorithm NEA2. The UE gets this command. It activates its own security functions with those exact algorithms, and then it replies with a security mode complete message. This reply basically says, Roger that. My security is now active, just as you commanded. From that point forward, all the other sensitive control messages, like the RRC reconfiguration and its RRC reconfiguration complete response, they must be cryptographically protected. By capturing this traffic and verifying this exact sequence of messages and what's inside them, testers can confirm with absolute certainty that the security protocols were negotiated and enabled correctly, just like the standard says they should be.
So far, we've successfully used our testbed to verify the fundamental security of the over-the-air communication protocol. That's a huge step, but it's really only one piece of the puzzle. Think about it. A network with a perfectly secure protocol that can't handle real-world user load is functionally useless. And likewise, a high-performance network that has gaping software holes in its management interfaces is just a major liability waiting to be exploited. So now we have to broaden our testing focus. We're going to shift our attention from the security of the protocol to the resilience and the security of the network equipment itself. This next phase of validation involves two very distinct but equally critical activities: performance stress testing and software vulnerability scan.
It is so important here to clearly separate these two different sides of the testing coin because they're answering very different questions. On one side, you have performance testing. This is all about load, scale, and resilience under pressure. The fundamental question it's trying to answer is, can this device do its main job correctly even when it's under extreme conditions? This is where tests like that 256-user attach storm we talked about earlier come in. Here, we are intentionally pushing the device to its absolute operational limits to see if it crashes, to see if its performance degrades gracefully, or if it just starts dropping users left and right. On the other side of that coin, you have security testing, specifically vulnerability assessment. This type of testing isn't concerned with user load at all. It's a meticulous hunt for flaws and weaknesses in the device's own software. The fundamental question here is, can this device's defenses be broken? Can its functions be maliciously manipulated? This usually involves scanning the device's management interfaces, like its web login page or its APIs, for known security bugs or common misconfigurations that an attacker could use to get control. Both are absolutely vital. A device that passes all its performance tests but is easily hacked is not deployable. And neither is a perfectly secure device that crashes under a normal user load.
Let's focus for a minute on that second type of testing: vulnerability assessment, or VA. The best way to think about this is like a comprehensive automated security checkup for your network equipment software. A VA tool, like the industry-standard Tenable Nessus that was mentioned in the source material, connects to the device over the network, just like an administrator or an attacker would. It then methodically runs this huge battery of checks against the device. It scans for open network ports, it probes web services for weaknesses, it tests APIs for known flaws, and it compares everything it finds against a constantly updated massive database that contains thousands of known vulnerabilities, common misconfigurations, and dangerous software defects. It's a proactive hunt for potential security holes designed to find and fix them before a real attacker ever gets the chance.
A really key part of modern vulnerability assessment is that when a scanner finds a problem, it doesn't just say, "Hey, problem found." It quantifies how severe the problem is by giving it a score using the Common Vulnerability Scoring System, or CVSS. This is a global, open standard that provides a numerical score, usually from 0 to 10, to rank the severity of a software flaw. And this score isn't arbitrary. It's calculated based on a whole range of metrics, like how easy the flaw is to exploit, whether an attacker needs to be on the local network or can attack from anywhere on the internet, and what the potential impact on confidentiality, integrity, and availability would be. Across the entire industry, a CVSS score of 7.0 or higher is the universally recognized threshold for a high-risk vulnerability. Any flaw that's discovered that scores a 7.0 or above is a huge red flag. It's a serious issue that cannot be ignored and has to be prioritized for an immediate fix by the equipment vendor. These vulnerability scans aren't just random probes either. They're highly structured and they look for problems that fall into well-understood categories, mapped to established industry-standard frameworks. Two of the most important and influential of these are listed right here. The OWASP Top 10 is a famous, regularly updated list of the most critical security risks that are found in web applications. Since almost every piece of modern network gear is managed through a web-based interface, this list is incredibly relevant. It covers critical issues like injection attacks, broken authentication, and security misconfigurations. The CWE, or Common Weakness Enumeration Top 25, is a broader list of the most common and dangerous software weaknesses across all types of applications that can lead to serious vulnerabilities. By scanning for issues that map directly to these well-known lists, development and testing teams can make sure they're focusing their energy on preventing the most widespread and highest impact types of security flaws.
Okay, so at this point, we've put our ORAN components through an incredibly demanding gauntlet of tests. We've verified their fundamental protocol security. We've hammered them with punishing stress tests, and we've scanned them for every known software vulnerability. All of this painstaking and, frankly, expensive work in the lab serves a purpose that goes way beyond just finding and fixing bugs. This rigorous, multifaceted testing is the essential prerequisite. It is the non-negotiable foundation upon which we can build the ultimate goal of the ORAN architecture: a truly intelligent, cloud-native, and comprehensively automated network. So let's now explore exactly how that critical connection is made.
This slide right here expresses what is maybe the single most important principle in this entire explainer. Testing builds trust, automation builds scale, and you simply cannot have the second one without the first. Think about it. No sane network operator would ever hand over the controls of a complex, multi-billion-dollar, nationwide network to some automated system unless they had absolute, verifiable trust that the underlying components were secure, compliant, and robust. And that trust isn't just some abstract feeling. It's an asset that is earned. It's earned through the thousands of repeatable test cases, the clean security scans, and the successful stress tests we've just been talking about. All of that methodical effort builds the deep confidence required to finally flip the switch on automation. And automation is the only way to manage the immense complexity and achieve the operational scale that modern and future networks demand.
The key technical enabler for this new era of intelligent automation is the RIC, which stands for RAN Intelligent Controller. This is arguably the most revolutionary and disruptive component in the entire ORAN architecture. For decades, like we said, the RAN was a closed black box. Its optimization logic was all hidden away by the vendor. The RIC is a cloud-native software platform that just blows that box wide open. It creates a standardized platform with open APIs, most notably that E2 interface, that allows specialized third-party applications to safely monitor, control, and optimize the behavior of the underlying RAN in near real time. These applications are called XApps for near real-time control functions that have to execute in milliseconds, and RApps for non-real-time control functions that can take a little bit longer. The most powerful analogy for the RIC is that it creates an app store for the network, where operators can deploy applications from a whole variety of innovative vendors to do things like save energy, manage traffic, or improve the user experience.
This presents a powerful and really practical example of the RIC in action, one that has an immediate financial benefit. Energy consumption is a massive and growing operational cost for every mobile operator out there.
A modern massive MIMO antenna, with its hundreds of individual radiating elements, is a particularly power-hungry piece of gear. So this is where an energy-saving XApp provides immense value. This specialized application runs on the RIC platform, and it constantly monitors traffic data that's being reported from the RAN over that E2 interface. During periods of low traffic, say in the middle of the night in a residential neighborhood, the XApp can make an intelligent decision. It sends a command back over the E2 interface to the radio, telling it to power down specific antenna elements that aren't needed right now, and that saves a significant amount of electricity. Then, as traffic starts to pick up in the morning, the XApp commands the radio to power those elements back on, seamlessly restoring full capacity. And this isn't just theory. As the slide notes, this exact use case was publicly demonstrated at Mobile World Congress 2025 by major industry players. Juniper provided the RIC, Remodo provided the XApp, and Keysight provided the test tools to validate the savings, proving that these applications can deliver significant, measurable ROI today.
Let's keep building our automation picture with another critical open-source project, Nefio. So if the RIC is the specialized brain for optimizing the live running network in real time, then you can think of Nefio as the automation engine for deploying, configuring, and managing the entire life cycle of the network functions themselves. It's a really powerful project originally started by Google and now hosted by the Linux Foundation that aims to apply modern, proven cloud-native principles directly to the complex world of telecom. Specifically, it leverages the power of Kubernetes as a universal infrastructure layer, and it uses a workflow called GitOps to bring an unprecedented level of automation and reliability to network management.
The real power here comes from the synergy of these three technologies all working together. Kubernetes, the container orchestration platform, has basically become the operating system of the cloud. It's fantastic at running and managing complex, distributed software at scale. GitOps is a revolutionary operational model that builds on top of that foundation. Instead of having an engineer manually log into machines to type commands and make changes, the entire desired state of the network, all of its configurations, its policies, its software versions, is declaratively defined as code in a Git repository. To make a change, you just change the code and submit it for review. Once that's approved, an automated process, which Nefio manages, detects the change and ensures that the live network is automatically and safely updated to match that new desired state defined in the code. This combination gives you a declarative, version-controlled, and fully auditable system for managing an incredibly complex, multi-vendor O-RAN deployment. Its greatest benefit is that it dramatically reduces the risk of human error, which is still the #1 cause of network outages, and it provides the powerful engine you need for true, scalable, cloud-native automation.
The vision we've just laid out, a fully open, intelligent, disaggregated, and automated network, is undeniably compelling, and it's incredibly powerful. But it's also important to be pragmatic and to be clear-eyed. A paradigm shift of this magnitude, it doesn't happen overnight, and it's certainly not without its own unique set of difficulties. As the industry moves into this new era of O-RAN, it's facing a set of very real challenges that have to be methodically overcome. But on the other side of those challenges lie opportunities that are just as significant, opportunities that promise to redefine the economics and the very capabilities of mobile networks for decades to come.
This slide gives us a fantastic, balanced view of the current landscape, a really pragmatic balance sheet for the whole O-RAN initiative. Let's look at the challenges first. Multi-vendor interoperability is both the core promise and the primary challenge. Making components from different vendors work together perfectly isn't a one-time thing. It requires a continuous commitment to rigorous testing and deep alignment with community efforts, like the O-RAN Alliance plugfests. Second, security and compliance are completely non-negotiable. In a disaggregated system, the potential attack surface can be larger, so the security posture for each component and for the system as a whole has to be even more robust, demanding continuous scanning and verification. And a fascinating new problem is emerging with the RIC, XApp conflict management. What happens when an energy-saving XApp wants to reduce a radio's power, but at the exact same time a traffic-steering XApp wants to increase its power to improve performance for a high-value user? This creates a need for new governance frameworks to manage these potentially conflicting goals. But the opportunities are just as compelling. The return on investment for mature use cases, like that energy-saving XApp we talked about, is immediate, and it's tangible, which helps operators fund the broader transformation. Cloud-native automation, powered by tools like Nefio and GitOps, fundamentally reduces long-term operational costs, and more importantly, it reduces the risk of those costly, manually induced outages. And finally, that powerful synergy between formal standards bodies like ETSI and 3GPP and the work of the O-RAN Alliance, it creates this virtuous cycle, a kind of flywheel effect
that accelerates market adoption and builds a more stable, predictable, and innovative ecosystem for everyone.
After our extensive journey through all these concepts and technologies, this slide really distills our entire discussion down into an incredibly useful and actionable checklist. This is the practical, high-level takeaway for any engineering team or manager who's tasked with implementing or purchasing or validating O-RAN technology. Let's walk through it one last time. For functionality, the key action item is to run that 256 UE attached storm, and the metrics you're measuring are the attached success rate and the connection latency. For security, the critical task is to verify RRC integrity. That means looking for that MAC-I field in your packet captures and making sure your system never, ever falls back to the dangerous NIA0 algorithm. For vulnerability, the required action is to run a Nessus scan or a similar tool against all management interfaces, and your pass-fail metric is ensuring there are no unpatched vulnerabilities with a CVSS score of 7.0 or higher. For consistency, the key is to test against the same official scripts used in the public plugfests and by the Open Testing and Integration Centers, or OTICs, to make sure your results align with the broader community. And finally, for reporting, the modern goal is to stop thinking of testing as this manual one-off process and instead integrate all your test assets, your scripts, your configurations, your captured packet reports, into an automated CI/CD pipeline managed through GitOps. This checklist really is the blueprint for a modern, comprehensive O-RAN validation strategy.
This quote serves as the perfect thesis statement for our entire deep dive. For a long time, the public conversation around O-RAN focused almost exclusively on the open aspect. You know, the ability to mix and match vendors to reduce costs and avoid getting locked in. And while that is undeniably important, it's really only the starting point. Openness is the means, not the end goal itself. The true, lasting value of this new architecture lies in what that openness enables. It enables a network that's transparent enough to be deeply and rigorously verifiable through all the comprehensive testing we've discussed. That verification, in turn, builds the trust you need to create a network that's consistent enough to be automatable, which reduces both operational cost and human-induced risk. And that automation ultimately creates a network that is flexible and dynamic enough to be sustainable. A living system that's capable of evolving to meet the unimaginable demands of the future. That is the real transformative promise of O-RAN.
And so, as we wrap up this explainer, we're left with this final, provocative thought to consider. The global shift to O-RAN represents a fundamental move away from a world of closed, monolithic, single-vendor systems to a new world of open, disaggregated, and intelligent ecosystems. This transition brings with it unprecedented freedom, flexibility, and innovative power. But with that great freedom comes a new and profound kind of complexity. The challenge for network operators is no longer just managing a box from a single vendor. It's about becoming a master systems integrator, orchestrating a dynamic and constantly evolving ecosystem of hardware, software, and AI applications from a multitude of different sources. The most important question we all have to consider is this: are the skills, the culture, and the operational tools of the telecommunications industry truly prepared to manage the complexity that comes with this new freedom? The answer to that question will ultimately determine the trajectory and the success of this technology over the next decade. Thank you for joining us on The Explainer.